This is the SAP6502 playing Apple II Pac-Man. It's a TTL CPU based on Ben Eater's SAP1, but with a few enhancements that let it run 6502 machine code. Here we can see the Microcode EPROMs, and the purpose of this series is to show how I came up with the code that goes in those EPROMs. In my humble opinion, this is slightly overlooked in many YouTube videos on how to build a CPU. What I think we're trying to do is somewhat akin to learning all the tricks of the puppeteer. The sequence of memorized maneuvers really brings the puppet to life. This is an annotated view from a 6502 die shot, and we can see a structure up here that's somewhat equivalent to a read-only memory or ROM. It's actually a bit easy to see the microcode store on the 68000 microprocessor. Leave a comment below and let me know if you want to see me have a crack at building one of these. The SAP68K. Back to microcoding, who invented the idea?
The man most directly responsible is Miles Bennett Dyson.
Actually, that's not completely true. It was the famous British computer scientist, Sir Maurice Wilks, that invented the microcode.
In a few months, he creates a revolutionary type of microprocessor.
Well, actually, the idea of microcoding is almost as old as the computer itself. Wilks first described it in this 1951 paper titled The Best Way to Design an Automatic Calculating Machine. Here's Wilks on the left working on the EDSAC, which is considered to be the second stored program machine ever made, and while it didn't use microcode, its successor, the EDSAC2, did. Let me read this excerpt from Wilks' 1951 paper. The matrix A contains sequences of microorders for performing all the basic operations in the order code of the machine. All that is necessary to perform a particular operation is that microcontrol shall be switched to the first microorder in the appropriate sequence. I want to start off with a high-level picture of how we're going to arrange the software for the microcode generator. We start off with the AppleWin emulator, links below, and this has been running for the whole series. I'm actually very happy with AppleWin. It seems to run all the code I've thrown at it. AppleWin maintains a number of internal variables which represent the state of its emulated 6502. Now what we want to do is build an emulator for the SAP6502 which taps into those very same state variables that AppleWin uses. I want to be able to swap between the AppleWin emulator and the SAP6502 emulator on an instruction-by-instruction basis. For example, let's look at this strip of code. The 90 hexadecimal is branch if carry clear, and we might want the AppleWin emulator to handle this instruction. Next is 18 hexadecimal, which is clear carry, and we want the SAP6502 emulator to handle this instruction. I want to be able to execute this piece of code and arbitrarily swap between the SAP6502 and the AppleWin emulator. This allows me to isolate individual instructions or sets of instructions for the new code that I'm writing. I don't want to build the entire thing, then try and debug the entire thing. If I can, I want to be able to build and debug one instruction at a time. Let's say I've built the instructions for load and store, but I haven't done add yet, then I can just seamlessly swap between the two emulators and get the code to run. The SAP6502 emulator quite closely represents the hardware that we've built, therefore it requires microcode to run. This leads us to the microcode generator, which is what we really want. The microcode it produces goes into both the 6502 emulator and the real hardware. In fact, the main goal of this whole process is to generate microcode for the hardware. In this series, we're going to focus on the SAP6502 emulator and microcode generator, and in reality, the microcode generator is the bulk of the work. In this video, we're going to be writing a number of new function calls. The first one is SAP6502 cycles. Now this is effectively just a big lookup table, but it contains the actual number of 6502 CPU cycles for the current instruction. a return 0 if we don't want the SAP6502 emulator to execute this instruction, and this is the main mechanism for selecting between the two emulators. This cycle count is really for the AppleWin emulator, which uses this information to keep its internal timing accurate. Emulate SAP6502 executes a single instruction using the microcode that we plan to use in the final machine. These two function calls form the basis of the SAP6502 emulator. In the next video, we'll start on the microcode generator. It has two set micro instruction function calls. These are overloaded where one takes a flag bit and the other doesn't. I'll explain these in a bit more detail when I actually write these routines. First, we'll focus on the TXS instruction. So we have an individual function call that writes the microcode for just this instruction. Finally, we have program control ROM. This generates the fetch and reset code common to all instructions, and it also calls the individual instructions like program TXS to make up the entire ROM. Remember that I wanted to be able to arbitrarily swap between the two different emulators. To be able to do this, we need to go deep into the bowels of the AppleWin emulator. If we dig deep, we see that it starts with continue execution, goes on to CPU execute, which calls internal CPU execute. This then calls CPU6502. This contains a do-while loop for executing multiple instructions. Inside this loop, we do the fetch, decode, and execute for a single instruction. After each instruction, it calls this video update routine. Now, this do-while loop goes for about 1,000 clock cycles or 46502 instructions. This is the main inner loop of the AppleWin emulator. The first thing I want to do is change CPU6502 so that it executes just one instruction. Then I want this do-while loop to be outside CPU6502 and at the level of internal CPU execute. The count of 1,000 cycles occurs here now. It means I have to call CPU6502 for each instruction, but I'm really not worried about that at this stage. Now, I can add some code that decides whether or not to use the SAP6502 emulator or the AppleWin emulator and switch the two different emulators on a cycle-by-cycle basis. It's the use SAP6502 function call that decides which emulator to use. Let's start looking at the real code. Here's CPU6502. Let's go ahead and insert the NTSC update code. We'll move the do-while loop to internal CPU execute. We need to keep track of the internal timing for this routine. We use this variable, elapsed cycles. I've modified the parameters in the call to CPU6502 so that we only get one instruction executed. Elapsed cycles represents the total number of clocks for this one instruction. There's also this interrupt handler, but Pac-Man doesn't use interrupts. Let's see if it works. Syntax error. Let me fix that up. The dangling else is right down the bottom. I just need to move this if statement. Alright, let's compile that and see if it runs. And no. Let's have a quick look at the code again. I need to update the cumulative count of executed cycles with the most recent instruction. Let's compile this again and see how it goes. Well, this is looking more promising. I always like to see the Apple II symbol. And Pac-Man. Excellent. I tend to use Pac-Man a lot, and that's for a couple of reasons. One, I'm pretty familiar with the code now. And two, it exercises most of the 6502 instructions. My first goal is just to get Pac-Man working. Let's start working on the code for SAP6502 cycles. Return 0 if we want AppleWin to handle this instruction. And to start off with, this will be most instructions. We need to do a main memory read to fetch the opcode. This pointer to mem plus regs.pc is where AppleWin is storing the code for the current instruction. At the moment, we're just interested in the TXS instruction, which has an opcode of 9A. So if our current instructions are 9A, we return 2, otherwise we return 0. In our inner instruction loop, we call SAP6502 cycles. If this is equal to 0, then we call CPU6502. Otherwise, we want to call our new routine emulate SAP6502. For now, I just want to test that all of this is working. So I'll manually copy the code that fetches the instruction, and if it's a 9A, we just copy the value in regs.x to regs.sp. We have to add 100 hex because the stack pointer refers to page 1. These are the variables that the AppleWin emulator uses for these 6502 registers, and it prefers for the SP value to be an absolute address. We'll compile that and see if it runs. We're not using Microcode yet, but I want to make sure that at least this works. And no. Let's poke around a bit and step through the code. We're definitely getting to emulate SAP6502, but it's still not running. Let's have a look. I need to increment the program counter as part of execute. Alright, this is looking much better. At least the pathway is now in place for the TXS instruction. Now I want to start emulating the controller sequencer itself. This is the architecture I chose, and now we want to look at the 40-bit control word coming out of the EPROMs. These are the signals I ultimately decided I needed. About half of them are used to control the ALU and status register. These 4 control signals require multiple bits each, so I'm going to use a bunch of hash defines to determine where they are in the control word. For any one clock cycle, driver tells us which register is outputting to the W bus, while load tells us which register is going to receive this information. The next 7 bits are individual signals we need to control the machine, and we're just going to define a mask for each of these signals. Hopefully you can see that they're just adjacent bits within the control word. Another signal which has multiple bits, so again we just define its position within the control word. The remaining bits are all individual signals, and all of these just use a bit mask to determine where they are in the control word. I used a couple of the remaining bits for PC select bar and for mread. This saved a couple of inverters, but they were spare bits. The lower 8 bits of the control word are different to the rest because these go through some 3 to 8 decoders before they start driving actual signals. The lower 4 bits control the output enable on a bunch of registers, while the upper 4 bits control the clock for the associated registers. We're going to need to capture this register ordering in our emulator. Again, we do this with a bunch of hash defines, and we enumerate all the positions of all the registers. You'll also note that I've defined this high Z register. This is the same as EAL because this signal isn't actually used to control the output of the EAL register, the PC select signal is. When we choose the driver to be 14 or high Z, then nothing's driving the W bus and it's high impedance. This lets another device like the memory drive the W bus. I could have used another value like 9 because the instruction register output enable is always asserted. Now we have the status register to worry about, so we just define the position of all the flags within the status register. Note that I'm using the U and P flag for bits 4 and 5, and I'll discuss these later. You might have noticed this flag bit signal. This tells us which address line the output of this 8-to-1 multiplexer is connected to. We're nearly there, we just have the ALU to worry about now. We have these 5 bits which control the function the 74HC181s perform. Addition, subtraction, logical AND, OR, and XOR. Now I need to define the bit code for all of these instructions, and again this is just to match the 74HC181. Now I need a data structure to store the control EEPROM. I've used G_control_ROM, and it's got 128k entries. I really should hash define the size rather than using a magic number. The 6502 has 256 instructions, and I want to keep track of how many steps there are per instruction. Finally, I need to set aside some memory for our register bank. That's what this 16-byte array is for, G_SAP registers. Alright, that should just about do it for setup. Next video, we'll work on the emulator and microcode for the TXS instruction. And don't forget to like, share and subscribe. Let me know what you think about doing a series on the 68K microprocessor.